it's my great pleasure to introduce John Pavlopoulos for the keynote lecture today. John is elected assistant professor at the Department of Informatics of Athens University of Economics and Business. And John Pavlopoulos is also affiliated with Stockholm University. Previously, he has been a senior lecturer at Stockholm University and also a visiting scholar at the Venice Center for Digital and Public Humanities at Ca' Foscari University of Venice. John Pavlopoulos has specialized in machine learning for natural language processing and digital humanities, and he is also a member of the editorial board of Magazine, International Journal for Digital and Public Humanities of the Venice Center for Digital and Public Humanities. Today, I'm very excited about the topic of this talk, which should also be very relevant to a lot of research that is going on here in Vienna. And this talk will be on machine learning for ancient languages, spanning the study of ancient texts written in any language, script, and medium, and spanning over 3.5 millennia of civilizations around the ancient world. With that, very warm welcome, and I'm looking forward to the talk.
Thank you so much, Ben. It's a pleasure to be here, and thank you for the opportunity. Without further notice, I should start, and exactly from where Ben left it. It's a lot of years. I mean, it's 3 millennia, but I should start with a survey. We need a reference point, and this is what we did. We did a survey for machine learning for ancient languages to provide such a reference point, and this took us to the next step, a workshop that has been accepted for the next ACL to take place in Thailand. So this presentation, this talk, we'll use these two as our basis, as the basis of all the material. And I will go into details, but first let me talk about this survey and how it's useful. So ancient languages are key conveyors and repositories of ancient civilizations. They encode several aspects of the past, as you may already know. And the texts that preserve these languages were written over the centuries on a variety of media, a variety of scripts. And we could say that similarly to how microscopes and telescopes have contributed to the realm of science, the humanities can now be assisted by machine learning. And over the last 20 years, advances in machine and deep learning, along with increased computational power, I mean GPU, have led to transformational advances in the study of ancient languages and texts, among others. Improving the state of the art in character recognition, stylometrics, author attribution, textual restoration, and many other tasks. So data are available, and they are publicly accessible. They have high-quality photographs, transcriptions of ancient texts. At the same time, machine learning is being advanced. For example, it is getting deeper and deeper. As a result, more people are inspired to digitize ancient texts and to explore new methods to study them. And this fuels a dynamic feedback loop, as the picture tries to convey. Competitions are a clear example of this. This is a trend, and it has a direct consequence. That is, new interdisciplinary research questions are being posed. And the growing number of publications per year, out of the ones that we surveyed, demonstrates this momentum. You can see this in this graph. So in a machine learning setting, ancient languages exhibit several differences from their modern counterparts. For ancient languages, often very limited data is available today, owing to low survival record, damaged state of material preservation, for example, inscriptions, or complex transmission traditions, as for literary texts. Moreover, only a small fraction of the extant ancient data has been digitized in a standardized open access and, I would say, metadata-rich format. And this is crucial to machine learning tasks. So written in a variety of writing systems, some ancient languages are now extinct. For example, the Mayan hieroglyphs, or they remain undeciphered, such as the Indus script. And what is more, a single script might encode several languages. But the relationship between these languages might be unclear. Even within the same script, or even, let's say, the same language, variations between genres and written supports, text types, geographically or chronologically specific variants, all of these hinder generalization of machine learning models. But the challenge for machine learning can be even bigger. Language-specific idiosyncrasy exists, like Latin abbreviations, as an example. And complex textual transmission history set another issue. For example, it could be disputed authorship. Furthermore, we have semantic shifts of words between ancient and modern languages. Agora, for example, used to mean gathering place in ancient Greece, but now it refers to something completely different. And this, combined with a lack of ground truth, as it happens for the restoration of textual lacunae or for the dating of a text, let's say, make evaluating a model's performance extremely difficult. But it is this very complexity that makes the study of machine learning for ancient languages a worthwhile research topic and an interesting benchmark. To best undertake the review work for the purposes of this survey, we designed a taxonomy following the different but not necessarily sequential steps involved in the study of ancient documents. Digitization brings textual sources to a high quality and machine-readable format, for example, through optical character recognition or handwritten text recognition. And restoration regards the process of recovery of missing text and reassembly of fragmented written artifacts. Then attribution is about contextualizing a document within its original geographical, chronological, and authorial setting. I mean, who wrote the text, when, where. And linguistic analysis involves linguistic tasks such as semantic analysis, part of speech tagging, representation learning, and segmentation. Then it's textual criticism, the process of reconstructing a text's philological tradition of textual transmission. And then translation and decipherment aim to make a text's language comprehensible and interpretable to modern-day researchers. So the majority of the surveyed articles operated on text. So the input was text. But there are studies for quality enhancement, fragment reassembly, paleographical analysis, and writer identification, which operated mainly on visual input, so on the image. Especially in digitization, however, there are studies harnessing both modalities. So next, in the slides, I will try to focus more on this. So let me provide a bit more of the context in this case. Handwritten text recognition, or HTR, is a well-studied area of research, and it's the first step in the study of ancient texts using machine learning. And that's because it makes this digitally accessible for downstream tasks. I will use this term. So we want digital text in order to work with NLP, with natural language processing, and other models that machine learning can unlock. Recognition pipelines then rely upon the existence of digital images. It's the first step. And to be successful, high quality and quantity of digitizations are required. Then image preprocessing, text segmentation, feature extraction and classification, and then post-processing. So I'll dive a bit more. I will focus on text segmentation. Several studies propose HTR as a classification problem of pre-segmented character images. But character segmentation is not a solved task, and especially in scripts, for example, where character boundaries overlap, as in cursive handwriting. So this is an example where interdisciplinary teams gain strength. If you took just the one, you wouldn't be able to come into concrete findings. And the challenge increases by the state of preservation of ancient written media, as by damaged supports or low-quality images. And there is a direct consequence. That is, other studies have chosen to approach the task more holistically by introducing pipelines that include handcrafted or trained alignment and segmentation models. So it's like a loop. Humanities, machine learning, going back and forth and improving. So now perhaps we can focus more on a specific study, falling under the scope of this topic, to get a better picture of what's in machine learning for an ancient language. So perhaps you may have inferred it already from the previous slides, but we can make it more explicit. Applying HDR, recognizing the text from an image, especially when the image regards an old manuscript, it's not an easy task. And it is why we observe a diversity in character error rate. There are many errors. And it's other lines maybe with few errors, other lines maybe with many. The diversity could be strong. It could be even scrambled text, giving no meaning at all. So while avoiding correcting the HDR output delays preservation and hinders further recognition, we need to solve that. And this is this first study. It's not HDR per se, automatically transcribing text from an image to a text. We're going one step further. So a reasonable hypothesis then is that the detection of an erroneous recognition is easier when the recognition output is scrambled compared to an output with a single, let's say, just one character being wrong. And that is automatically detecting whether the HDR output is correct or not. This is an easier task when you have a lot of errors in the text. It's easier for the eye, for the human eye. It's easier for a model. To give an example in the right context, classifying recognized text as erroneous or not is easier in the right case and compared to that on the left, at least for me. Detecting erroneously recognized text can improve automatic error correction. Let's say encoder-decoders, for example. Let's take a flawless text and give it to encoder-decoder. It's a likelihood, it's highly probable that the decoder might paraphrase the text and introduce errors. So I should do a pause here and say that this study focuses on one language, on one ancient language, and that's the Greek language. But is it ancient? It's only after the first millennium. And this is a vague point. But this doesn't make it out of scope. And that is, as time progressed, elements of contemporary spoken Greek gradually became integrated into what was called Atticized Greek. And as the results of this study will show later in the slides, pre-training on modern and then ancient Greek is beneficial for text classifiers detecting incorrect recognition output. And when I say pre-training, is like taking the best of both worlds, of both languages, putting them inside the model, and then using the model as a starting point for machine learning. And trying to go from slide to slide, pointing to different studies, and making a single line, a single narration that would go from the survey to the workshop. We use transcriptions that were published for a challenge, a recent challenge, the purpose of which was to post-correct erroneous HDR output. So the transcriptions and the HDR output come from HREC, and the language is Byzantine Greek. Selected images of handwritten text in respective manuscripts, and these were from the 10th to the 16th century, were transcribed both by human and an undertrained HDR model. So we have the correct, let's say correct, the human transcription and the system recognition. And this is parallel text. So now we can go on and investigate the character error rate per century. And what this diagram, what this graph reveals is that we don't have the same error, we don't have uniform errors over time. Specific centuries were more difficult to recognize the text from images. But our purpose is different. So we want to set up a classification, a text classification, a concrete NLP task. That is, we train a classifier. It's a black box. We don't care here. It could be anything. And then we want to give it a text, a transcribed, as you can see in the white box, which is either transcribed by a human expert from that image or by a system that did HDR. And then the classifier will say, it has errors, it does not have errors. In the use case I introduced previously, if we want to pass this text to a post corrector because we assume it has errors, it would be beneficial to have someone saying, no error here, don't give it to an encoder decoder, don't do anything, it's fair. So this is the setting. And what we did is we took the red data, the recognized, the ones that likely have errors, and we took the green data, the human transcriptions. We used this whole as training data, we trained the classifier to learn to predict whether a new text is erroneous or not. In this case, it said that this is correct, and it is, but this is a hypothetical case. So I'll dive a bit into the results of this study in order to give a hint of the benchmark. How could an analysis of text classification, NLP, machine learning results meet the analysis of an expert? So a random baseline here, a system that predicts at random, draw the lowest performance. And this was outperformed by conventional machine learning models. And the best was an MLP, a machine learning, an MLP that performed similarly to a recurrent neural network, whoever knows it, but this is just introductory to say the next thing. We focused on BERT. BERT is famous, at least in NLP, and it's a transformer that is, as I use the term, pre-trained on many texts. So what we did here is we took a transformer that is pre-trained on modern Greek. And then we took another transformer that is pre-trained on modern and then further pre-trained on ancient Greek. Let's say that we hide a token and we hide the word and we ask the model to find what word was it. So it was first we were hiding words in modern Greek and then we went into ancient Greek. So it learns kind of both languages, if I may say simplistically. And what we see here is that the deeper and pre-trained BERT models are better, and this was expected. But further pre-training in ancient Greek is the best in all metrics. And this is probably because it combines language elements found in both ancient and modern Greek. This was kind of expected. But then we thought, can we see why we had already some hint that time matters? Different century, different results. So how could we segment this result into gain a better understanding of what the results are? What can we do with HDR? How do we handle different errors from different centuries, and so on? So what we did here is we grouped the test lines, the lines that were used to evaluate. We grouped them based on the century, the manuscript they came from. So we have lines coming from manuscripts from the 10th, 11th, 16th century CE. And we evaluated the two transformers. The pre-trained in modern Greek, shown in light blue, and the one that was further pre-trained in ancient Greek, shown in light red. And we see that the classification performance depends on the chronology of the manuscript, with older manuscripts being better handled by a model that was further pre-trained on ancient Greek. On the other hand, lines from recent manuscripts pose an easier classification challenge. So the more recent, the better both models were, which sounds trivial, maybe. So we thought about it, and these 3 centuries are more challenging in HDR. Studying literature, we see that there are more errors in these 3 centuries. And what that means is the more errors in the recognized output, the easier it becomes for a classifier to distinguish an erroneous line. So everything connects. This is the point. And everything can be explained. But what I would like to convey is that only an interdisciplinary team could have unlocked this. We had to discuss with experts, with papyrologists and paleographers, and machine learning experts were then giving the results, and there was this loop. But we did another thing. Although class balanced, this dataset remains imbalanced at the character error rate. As already discussed, there is a diversity of errors, and that's natural. The papyrus may be damaged, or maybe there is ink all over it. So some lines will be correctly recognized, others will be scrambled text. And this is a diversity you see lower in this image, in this histogram. So by creating character error rate zones, similarly as we did for the centuries, we could go from low to high and see the performance of the two models. So we segment differently now, and we try to understand the performance. And what we see is that high error rate lines appear to set an easy classification task to both models. So performance increases as the error increases, and this is reasonable. Similarly, considering that lines with a high character error rate comprise many errors and are hard to parse even by humans. The characteristic, however, makes them easier to distinguish from flawless lines, which comprise no errors from the recognition. And low character error lines, on the other hand, suggest a different picture. So low character error rate means small differences, few characters between the two types, flawless and flawed, and this makes the classification task far more difficult. So in this zone, further pre-training on ancient Greek had a bigger impact compared to zones with higher error rate. This is common in machine learning, so I'm making a pose to ones who are used to machine learning. If you use a single score to evaluate a model on a data set, so you have a machine learning model, you have a data set, and then you compute the result, the performance on every instance of your evaluation data set, then you compute a score, and you say this is the performance. But this is kind of too distant, too far away to get a result. Perhaps you should be focusing inside. It's not rule of thumb, one score matters, like AUC or so. So this was different, and we had to dive deeper in order to make something out of it. So the classification brought us some interesting findings, which wouldn't have been easy to unlock outside this interdisciplinary team. The same stands for explainability. We undertook an error analysis task, and in this case, we asked experts to manually evaluate lines and compare with model outcome. So for this line, for example, the model mistakenly classified it as flawed. It said, no, it's not right. Give it to an encoder-decoder. Judging from the network's attention, it's a way to let the model explain. The rare word phylakoluthos here has two accents, one at the O and one at the O at the end. And these confuse the model. So the subword with the second accent that you can see attracting more attention underneath is probably due to that. So the model is probably not exposed to words with a double accent. So we get an explanation. Perhaps we are getting a direction how to improve our model. Another example comprises the word Ismailiti. And before I say anything else about this slide, I should say that this was not clear to me after many parses of this thing. I was seeing and I was not understanding why. But after many parses, I could, and then I made this slide because I think it is worth it. So this was considered as a misspelled outcome by the classifier, but not by the experts. So we give it to the classifier, and the classifier always say, yes, there is a mistake. Look at this word, subword, sorry, and look at this subword as well. There is a problem. And then we give it to the experts, and they all agree, no, this is correct. This is absolutely correct. And then if we focus more on what the network said, where the problem was, it focused on the article. So the first one is the article, and it gives a big focus, it attracts a lot of attention. Then it's the last subword. So Ismailiti is a word, could have been a correct word. So the expert is right. But the network is also right, because then this is singular and this is plural. And the model is not used to this. So the model says something's wrong. Well, the truth is somewhere in between. Probably this is a corrupted line where a small subword is missing, and this is what the network took on, and the experts took it as granted. Yeah, this is the word, it's fine. So in this case, the expert should have known how the model works in order to understand why it uses attention. And of course, we needed the evaluation, the analysis, and we needed to focus on this example, in this very example. I have many more other cases for error analysis, but I would like to keep it short in this point. So I will change now to a different box. Because it will also allow me to talk for Ithaca, and this is joint work with Jan Sassel, Thea Sommersild, and other colleagues, and it combines nicely these two boxes. And what Ithaca is, it's a neural network that not only restores missing text, kind of like the transformer I told you before. So we have a BERT model or a transformer, we hide a word and then we find it and we let it learn the language. This could be done to restore text. Well, it's not that simple, of course, it does many, many more things, but not only this task, it also attributes the chronology and the geographical estimations, along with explanations. And as it is being described in the article, Ithaca's design, decisions, and visualization aids made it easier for researchers to interpret results. So besides what I talked earlier, I put the focus on evaluation, on how we collaborate in doing research. Now I'm changing it a bit, and I'm saying that we could use machine learning to improve the accuracy, but the accuracy of the experts. So for example, ancient historians here achieved 25% accuracy when working alone in restoring ancient texts. But when using Ithaca, their performance increased to 72%, surpassing the model's individual performance and showing the potential for human-machine cooperation in advancing this historical interpretation. And, well, it could also be used for current methodological debates, but I should point you to an interactive version of Ithaca Live, where there are more details about this, where this slide and the blog will probably tell it better. And instead of going into more details about how Ithaca works now, I would like to focus on something else. So Ithaca is operating on text, on digitized text. And this is a digitized text of inscriptions. And it also has a text classifier to predict the decade. But this is not the only way. In these boxes, the studies, so let's say that someone submits work to the workshop, it doesn't have to be digitized text, because digitized text does not exist a priori. It needs to be digitized and so on. So a different path is for the same attribution task, and for example for Papyri, and instead of inscriptions, and using regression, for example, instead of classifier, and using the image instead of the text. Directly have the image. Why go into digitized text if you can read the image? So I will use the remaining slides to focus on two different studies that elaborate on that, investigate the feasibility of this task. The first of these presented a machine-actionable dataset of around 400 documentary Greek papyri containing texts of various aspects of daily life. And that's letters, contracts, receipts. And what it also benchmarked chronological attribution, dating, using the transcriptions as input. So similarly as before, the text is the input. And applied a committee of models on manuscripts for which only the upper date limit is known, an ensemble. So going directly into the results this time, we used again the two transformers we saw previously, but now for a different task, and that is to estimate the date. Again, the model that was pre-trained not only on modern but also on ancient Greek gave better results, as is shown here, by the error, which the lower is the better. So lower error, better, and this is for the ancient and modern Greek BERT. Image-based vanilla convolutional neural networks were outperformed by a pre-trained fine-tuned for this dating task. And this is good, theoretically, but the estimated error was consistently more than 100 years for both. And this is not good. I mean, this is not good enough. It's more than a century. Ithaca, which was used out of the box and which was trained and focused on inscriptions, not papyri. And it performed better by the image-based baselines and was comparable to the fine-tuned BERT. And this is interesting because it's a path to talk about transfer learning, if you have heard it. It means you can take this network, Ithaca, and further train it or fine-tune it. We have a hint that this might be better than everything we see here. But we didn't do this here. Might be future work. Regression with extra trees here achieved the best results in all metrics with a mean absolute error of around 50 years. And let's try to better understand the error. This is the single score that I just discussed. It's an error that's been paraphrased, described as approximate years that you will fall out. But the predictions and the ground truth can be rounded. So we took the estimate of the years and we rounded it to the century level. And this means that we can evaluate it as in a classification setting. So in a classification setting, we have a confusion matrix. And what a confusion matrix says is that we have vertically the predictions, what the model predicted, and we have horizontally what it should have been predicted, was the ground truth. And now we can see the confusion, as for example, we can see that it said a specific value when it should have said something else. It can direct us to study more, to do error analysis and focus. But at the end, we want many high values at the diagonal. So we want the model to say the right thing. And this is what we look. The best result is achieved for the first and second century. And we can also see this by classifying per century. I'm missing a figure here, but I would like to put the focus on the end goal, which is the help of the experts, as was said with Ithaca. And in this study, we use a different tool. This is very useful when you have few texts. And in ancient languages, for ancient languages, we often have few texts. So what do you do when you have very few texts, like here, 400 only? In this case, we use a setting called the leave-on-out cross-validation. We took one, we trained on the rest, and then we evaluated on that one. Turn it around and go on until you have one model per instance that you evaluated. In this case, we built a committee of around 400 models. And we took that committee, and besides reporting the results, we said we now have also an ensemble of models that we could use to evaluate other cases, perhaps cases that are debatable, or perhaps use cases, cases that other people may be studying qualitatively. So we applied this committee to use cases that present different types of dating challenges. For this request for transfer of taxation, to give an example, which does not come from Egypt, it comes from Petra in Jordan, and many of the words found in the text are infrequent in Egyptian manuscripts. And on Egyptian manuscripts, the model were trained. So the date mentioned in the papyrus is second indiction, which refers to the second year of a repeated 15-year cycle. And the year 538 is relative, since it could be the second year of the previous or the next indiction. This year is logically deduced by the editors in this case. And apparently the models overcome the geographical variation by dating this manuscript between 521 and 575 CE. And we have a second use case. This regards the application of a trained model, in this case a committee of models, on manuscripts for which only the upper date limit is known. So we know until when. It won't be more recent than that. So we use a committee, and since we get many predictions, as many as the models, we have a population, we have a distribution. So we can yield a minimum, a maximum, and an average. We get an approximation of what the models say. And there are estimations that fall far from the upper limit in red, while others fall close. The estimated date from our regressors committee, however, should be read along with other information. And this is kept in the shared corpus, such as the place settlement. The figure on top right shows the frequent places, and we observe that in some places, the estimated dates fall closer to the upper limit compared to others. So apparently there is some explanation that we could focus more. We didn't in that study, but there is plenty of room for improvement. But one thing still remains vague, and what do we do when the input is image and not digitized text? I talked about it before, but now again, I give text as input. So in this final study, we will see this case where the task remains the same, attribution of the chronology, but the input is text images. So now the data, we change also the data. They are not documentary, they are literary. And usually, literary papyri do not bear a date. So consequently, they are dated based on paleographical methods. This means that the ground truth regards broad approximations which often span more than a century. Digital paleography, however, moved beyond human perceived features, quantifying the angle and direction of writing. By using the visual input, then, the next slides present a convolutional neural network inspired by this that is based on a focused augmentation strategy along with an explainability study. So we took a simple network and we tried to be inspired by how papyri look, how fragmented input look, and try to inject it into the training of a machine learning model. But first thing first, we need data in order to train a machine learning model. In this case, we only have 242 images. This is too few. The focus was on the 4 centuries, which made it even fewer. And we had to overcome that in order to train. So we could train on the whole image. It didn't work, of course. We knew it before, but now we tried it and no surprises there. So we tried to work on patches, but patches take, it's like breaking the text into small parts and not making sense, because if someone gives you a part with broken lines, you won't be able to understand. But then there was a breakthrough by a student who, during an assignment, basically, he suggested to segment the papyri and make thousands of images in that way while maximizing the information that could be given to a model. So automated segmentation is feasible, noisy, but feasible. And they remain a lot, they remain many, even if we filter out low quality images. So again, we get around 3,000 images. So as said, the method is a convolutional neural network, quite common as an approach. It's not the novel thing to do. But it gets better by adding synthetic fragmentation to augment the data during training. So we use the network in this case as a baseline, saying this is the backbone model, and we are going to try something different. Papyri are often fragmented. And this leads to partial information in the image to be dated. Instead of looking at this as a problem, as a weakness, we try to model it. So this pattern can be part of the augmentation strategy by simply erasing randomly imaged fragments that look like broken parts. So based on this augmentation, we saw that both CNN variants, a classification and a regression variant, performed very, very well for the task of dating images of lines, of text lines. At least in our research, this was a breakthrough. And despite the fact that both FCNN variants are trained on the same data, we note that we do not consider them as competitors. So the regression-based variant of this network suggests a specific year, a specific date, which can provide a very rough estimation of when the papyrus was written. On the other hand, the classification variant suggests a century and yields a scores to indicate its confidence. So it's like the network saying, it's very likely that it comes from this century, while the regression says, this is the year, this is the range within it falls. And since our end goal is to assist and not supplement the expert, we use these both in an explainability study presented in the next slides. Here, the heated colors in red show that the network consistently focuses on the letters in order to yield its predictions for the date. This is good news, because we want it to focus on the letters and not on the background or on noise. It could be also the distance between the letters, the size, the intensity of the ink. But it looks real. It looks like something that the paleographer might have looked into before dating. By contrast, it seems invariant from background noise. And it is also invariant from other attributes, such as holes, which are often present in these items and which do not get any attention from the model. So far, so good, because everything adds up. Everything makes sense. But we wanted to better understand the network. So what we did is we fed it with test images, augmented, with randomly shaped black and white patches. So the idea is that if we hide parts, if we destroy parts, what does the network see? And we observe that the model's focus changes according to the color of the patch. So it's not the same. If you mask the image with white, it's not the same as masking it with black. While white boxes appear to be disregarded by the model, black boxes are receiving much attention. So for white patches, the focus is everywhere except from that patch. And this is in line with our findings about the holes and gaps, also depicted in white in the papyri images. By contrast, the black patch affects the prediction as if there was a letter or as if the black color of the patch was ink, like thrown over the papyrus. In this case, it could have been that the network tries to see the letter, tries to understand what's between or what this stamp is. So, as previously, we can use this network to study unseen items. And in this study, we focused on 11 papyri that were vaguely dated as either to the second or the third. So now it's not like not after the third. We have a rough estimate saying it's either 2 or 3. And we asked the variants about them, also to see how the two networks, how the two variants collaborate with each other. So the classifier variant agreed that most of the lines in this papyri belong to these 2 centuries, which is reasonable. By averaging then the century probabilities across the text lines per fragment, we see that for the classifier variant, the 3rd century is the most likely date in most papyri. So we are starting to get estimations out of it. But the 2nd is the most likely in 3. And then we move to the other variant. So we have 2 types. The regression variant, on the other hand, provided us with a more precise chronology for the same lines. So we focused on 2 of these 11 papyri, and these were selected by the experts of the team. So the predicted dates for the lines of 1 attributed by the classifier variant to the 3rd century are diverse, and the majority falls on the late 2nd and early 3rd. So that's a different way to estimate, to get, again, a similar estimate. The other comprises parts of a poem by Callimachus and is dated from 150 to 250 CE, with the first editor arguing that it is the late 2nd CE. On average, our predictions suggest 200 CE, but some lines are predicted as early as 100 CE, while others as 250 CE. So whether these estimations are correct and how we could use it to back or fight opinions out there is the material of another study, which is on its way and hopefully will get results soon. So to conclude here and leave plenty of room for discussion or use material from a huge appendix I've kept. I don't want to go over the various findings presented densely here, but I want to keep the main idea. So machine learning for ancient languages can grow further, and it can grow in several directions. Hopefully, our survey will serve as a reference point. And the forthcoming ACL workshop this summer can present the next steps in these directions. Please spread the word and consider submitting your work so that we can continue this discussion in Thailand. That's all for me, and please, I'll be here for questions. It would be my pleasure to engage in a discussion. Thank you for listening. And that's an excellent question. I would say that's the topic, that's probably what many researchers have now in mind for the ACL and NACL conference. But I would start with Ithaca. So we've seen different types of explainability, different types of use cases. So in this case, we get a range of predictions. So we have the average date along with likely other dates. And we also see explanation in terms of the input. And the input is text, so we get highlighting of the words included. So the idea is that if you give this to the expert, you are not implying that what the model says is correct. You are giving the whole thing. Perhaps the expert does not choose the average, but we don't care. The idea is for the expert to choose the right thing. And this is the key. If you provide with the whole interpretations or the explanations, then the idea is that we want the team to win. There are researches, there are studies that do not make this assumption. But this is Ithaca. That's one. We also saw though not very clear, that we chose the word indictionous. In this case, again, we use explainability. And we provided the expert with all the highlights, what the model used to suggest the date. So the expert said, oh, okay, then if the network focuses on this word, then it's likely that this word, oh, yes, this is right. And this is what we want. So we want it's like using the prediction as a proxy to understand what happened. So we don't really care about the date, it's a trend, but then the explainability is the real thing. So I definitely agree with what you're implying, Ben, and I augmented, I'm going forward that we need more ways to collaborate with explanations. And then we have a more concrete case to answer the question, and this is with this explainability. So in this case, before going into this study, so how this works is like, we take the network, we get a prediction, and then we ask, what are the pixels that you focused more in order to predict? But before doing that, we wanted to engage into a cycle with the experts. So we provided them with explanations of the model, and we asked them, do they make sense? And we try to create a human-computer explainability method, in a sense. So this is just the start. I would say that explainability could even be used, if I may dive into more ML, in a reinforcement learning setting, not only to improve the results, but improve what the expert would like to see. So I circled the answer, not directly, hopefully to give more feedback. Yes. Well, thank you, because this will take me to the appendix that I really want to show. So it's not simple, so I have to also advise my notes. So in this case, we want to focus on the language. And the written language of the manuscripts and this papyri used is Byzantine Greek. or medieval Greek, or anyway, it's the language that morphological categories such as the optative, the plurifact, and the perfect have disappeared. So they just started going away. And others, such as the dative case, have gradually decreased. Infinitives and participles are still there in the texts, and kind of as reminiscence of the classical tradition, kind of, let's say. Encouraging one to treat the language as a unique variant, different from modern, and from the other hand, there are several spelling conventions that deviate from the other orthographic rules, while the ancient punctuation signs are still in use. Albeit not always with the same function. So I would say that following classical and preceding modern Greek, this language can be considered not a combination, but a variant that would benefit from using models that have seen both. So having said that, I'll jump back to the results and try to explain them. We have a big jump from the RNN to the modern Greek BERT. But what a modern Greek BERT is a transformer, so a big neural network, that is pre-trained on texts in modern Greek, and then it's fine-tuned on the data we have here, so in Byzantine Greek. So we are employing transfer learning. In this case, it worked. Reasonable. But what this table says that if you had pre-trained it not only on modern but also on ancient Greek, it would have worked better. So I would say, summing up, why did it work on modern Greek? Because there are similarities in this language, and transfer learning worked. So while fine-tuning, it worked reasonably well. But we get another finding. If you had used a better pre-training, more closer to the language that you're using, then you would have got even better. But then there is, what are you looking for? So if you're looking for good results, then you could have used the modern Greek, fine-tune it to the data you have. That works. If you want the best results, then you need to do it all. I would say not at all. I would say you should love ancient Greek authors in order to do it, or study ancient Greek and don't hate it. So it's a complex thing. I know that I'm not I learned in school, but if you talk to me in ancient Greek, I will probably not understand you, and though I have tried. So not sure if you're implying this, but there's definitely no ancient Greek in modern Greek. So the modern Greek BERT hasn't seen ancient Greek at all. So in this case, the input is fragmented. Not only in this case, but in this dataset. So we have instances that are missing information. This means that the model could learn to use the shape, for example, in that image, and this is something we don't want. The other is that we want the model to be able to predict even when information is missing, and not only because we have a limitation in our data set, but maybe also because we want the model to generalize to new data. So this was the intuition, that we should not use these holes as a problem, but we can create new. And while creating new, what you are effectively doing is you are creating new data. So if you break the image, if you hide the image, you are changing the image, and then the model learns to generalize. So it doesn't use all the information. You hide some information from it, and it's a new thing for it. So I think it has multiple aspects. I would say that an ablation testing should be used to measure the intensity of each factor toward a good result. one way is to incorporate it as a feature in the model. So try to predict not only whether the text is correct or not, try to predict the date. So what this would bring us in this case, connect two tasks. We talked about dating, the second part of the presentation. We talked about erroneous HTR detection on the first part. So the question is, why not do both? That's an excellent question. I think that's one of the future work I would like to see as follow-up studies. My guess is, well, following the same line as these studies, I would not only be interested in seeing the benefit from making not a single task prediction, but a multitask classification setting. I would try to see how much you benefit per task. So try to measure how much you benefit to the erroneous text detection from adding the time, but also how much you benefit from the erroneous text detection, if we are in the transcript text, in the dating task. So I would say you would combine two incomplete solutions and perhaps get an even better solution per task, maybe. But that's an excellent question, yeah. Future work, hopefully. I guess and hope so, in a nutshell. But I should elaborate much, much more for this question. So we talked about HTR when we started. And that was systems that automatically transcribe. They don't do it well. I recall 10 years back, they were far from good. And the last 5 years, probably following up the momentum we saw in the graph of machine learning and instant languages, we see e-scriptorium, transcribus, we see collaborative efforts, publishing models, publishing data. Yeah, because the key here is that this collaboration, and I think we know it now, will unlock benefits for both. So if we don't have good recognition models, then the human experts will not be able to transcribe many data. And without many data, we cannot train good recognition models. So that can help the experts transcribe more. So there is a loop that is broken now. And it's not broken because the experts and the machines are not collaborating. I would say that it's a matter of time. And I can see the momentum in recognition. There are a lot of ideas. One of these ideas is, for example, do not just recognize text. As Esteban said quite wisely, you should also add the date inside. Do you have the geographical information? Add it. As Ithaca suggested, you don't have it, predict it and let the people, the experts, come inside and help. And then we can produce more data. And while we produce more data, we increase the probability that we have models to help us to produce more. But I should say there is a limit. And the limit is that I don't think we will ever get, at least in the next 5 years, very strong models to help us create as many data as we need. Because there are many languages. The time is far beyond. I mean, it's not 10 years as we use now data. It's centuries. It's thousands of years. And the language evolved during that time. We take a word, and as we move, over time, it changes its meaning. So this should be taken in consideration for the models doing recognition, doing dating. Trying to understand the language means that you really have to do it, and you should make it in good context. So I would say it's very complex. And copying from what I said initially, this is also why it is challenging. And this is why we hope that in the workshop, we will cover all these directions. This is one direction, and it's the starting. Maybe, hopefully, next year, we will build on what we saw this year, I mean, the summer, and suggest, propose, learn from what we saw in order to help more. But to the moment, I can see the point, I can see the problem. Collaboration is key, and there is a momentum, but hopefully it's exponential one. So next year, we will get better machine learning models, more data, and better predictions, less time consuming from experts. Well, large language models. So the question is, where is generative AI in all this? Where are the recent large language models that do it all? How can they help? And I would say, first, we get potential from transfer learning. Large language models have better capacity to adapt to ancient languages. I mean, if BERT can do that, imagine a large language model trying. So perhaps we don't have to train them in data that we don't have and we will not have in the nearby years, in the following years. But perhaps fine-tuning or finding a way to inject them knowledge. And at this point, I should bring us help two concepts. One is retrieval augmented generation. This is something that now starts. It's at its starting ground. I can see the papers. And it could be used in the concept of ancient languages. We have many databases. Trismegistos is one if we go in ancient Greek, but there are many, many other. And we could build a huge database to use. And this will probably help with explainability as well. And also trustworthiness. We trust these models. So that's one way. The other way, hopefully, is to directly ask large language models to see what they know. So I did not use a large language model in the studies, but I could. I hope that in the next months, in the next years, people will do, because we are talking about retraining, fine-tuning, further retraining. How do we know that they don't have some capacity to get it quickly already? I don't know. Probably not, but why not try? But yeah, very good question, and hopefully we know by the summer. Well, that's a great question, because this is one aspect I completely disregarded in this presentation, but it's a key. I mean, it's basic for this presentation. How do you get digital images, since you're doing this study? How do you get transcribed texts? So I should say that in Ithaca, for Ithaca, we used a big data set that behind its development, there was a lot of work, not shown here. For the study on dating images of texts, there were people annotating by hand. And basically, this is an opportunity. This question brings an opportunity to elaborate on one more thing. In machine learning, it's not enough to have data. So it's not like you'll give it data and they will work. There is a concept called machine-actionable. So the data may be there, but someone needs to transform them into a form that can be used. And now to answer the question, there aren't any such language resources. So for each of these studies, we had to do it from scratch. Someone who had to do it semi-automatically and try to bring it into the right format to allow the models to learn, to allow machines to learn on these languages. One case was Trismegistos. So there are databases that have the raw material, the source material, in a good format, but they need to be processed, to further processed. Also, Ithaca was based on a previous study by Thea Somersil that it's called Pythia, and elaborate on that effort. So to summarize, we need more machine-actionable, publicly available data sets, not only data. Data exists, but we cannot really let machines learn on them unless we transform the data into the right format. And this is far from simple. I see inception in this question. So to repeat, under-resourced languages and endangered languages, for example, it's a big topic in NLP. We want to help them. We want to not only not let machines and NLP models work only for well-resourced languages, well-supported languages. I would even go to resource lean, not necessarily endangered or zero-shot scenarios. So where is this in ancient languages? And I would say that now we have, for example, endangered languages today. But this happened at every instance of the history. So there were endangered languages 100, 200, 500 years ago, 1 millennium. So languages were evolving and were dying. And this is very hard to model. It scales exponentially in order to be able to get it. So the challenge to get information out of it is not easy, but if we could do it, then the benefits are clear. There is a direct relationship with what you suggested. For example, languages share properties. We could use it. And I gave a presentation for one language. But as we said, there are many, many others. What are the common patterns? And I'm not talking about linguistically patterns. No, I'm not talking linguistic patterns that someone will study and reveal out of qualitative analysis. I'm talking about the patterns that a machine learning model could use to quickly grasp from resources from one language and use them for another. I think this is a very interesting topic for study with very few resources to study it. But I can see the benefit from trying it out. I see the relationship, I agree. Very difficult problem in my perspective. Well, one plan that didn't, unfortunately, I left out of resources, time, and I planned this HREC challenge, error correcting, the HDR output. This was for Byzantine Greek, and my plan was to do it for other languages, and I was aiming for Asian languages. So, but unfortunately, this was the first workshop, but it didn't follow up. That's in my hidden agenda at some point, and so far, following up from the question before, it would be interesting not only to create from scratch new models, but try to see what kind of transfer learning from what language to what language works best. Well, from a data-driven approach, let's say that we take a computer scientist and we give that computer scientist many models, one per language, and we give that scientist also data, and we allow transfer learning from model to model. Then we could even have some kind of estimation of the transfer learning that works. I think there have been such attempts from the Transcriptions and the Scriptorium team trying to suggest transfer learning from language to language. Unfortunately, I haven't tried it, so I wouldn't know for moving from Ancient Greek to Asian, but my guess would be it would be extremely hard to work. I would say it's like working from scratch, but that's a wild guess. I haven't tried it. Thank you for the question, though it's, I think it's another future work we should be working on. Properly estimating transfer learning, not only for assessing what kind of pairs of languages should you use for, but also to create more models and more accurate models for more languages, especially under-resourced ones.
All right, then with that, let's thank
Thank you.